Hello everyone. Today I'm going to discuss about the transformer architecture, how what kind of layers are in the transformer, and we'll go into each layer and understand deeply how the data flows through each layer. So before starting that, I'm going to tell you about this website where the architecture is described very beautifully. This is the website hosted in GitHub. You can go into that. You can go to this link. I'll provide this in the description. You can check this out. So if you go into the website, it will open this. If I refresh the website, it will show the flow of the architecture. I'll go each layer by layer and try to explain what each layer does. So as you can see, this is a model which is hosted in this space, that is I think GPT-2 small model, uh, and this is a pure transformer layer. It doesn't have any other kind of blocks, like concatenated blocks with transformer. Let's dive into the architecture, what happens here. So if you move your cursor, keep your cursor on this, for each word, this is a vector that is 7, which is 768 dimensional. This 768, this is a matrix, 1 by 768 matrix. It has 768 values. So each of the word has 768 values, and this 760, this embedding, if you click on this, it expands how this embeddings got generated. So this data, so let's go token by token. So first token came data. So it has this token embedding generator. This converts the tokens into numerical representation. Each token has a different number, IDs. So this data word has the ID 6601 and so on for other words. Then it adds a positional encoding for each word. So for data it is at 0 index, and for visualization, that is the first index, and so on. And after that you will get the embedding, which is 1 by 768 vector. So this embedding goes into, so if I click here again, it minimizes, and then it goes into this attention layers, each attention layer. So if you click here, this is the embeddings are all the words embedding, that is 6 into 768, that means 6 words are there, and 768 6 tokens are there, and 768 is the dimension, embedding dimension of for each token. And after that, there is a matrix, key, query, and vector. This is the main matrix which is in the attention layer, q, k, v. This is query, key, and value. So this is a matrix which has the dimension of 768 by 2304. So this q, k, and v, these are three matrices. Q is a matrix which has dimension of 768, and across 768, 768, and three matrices are there, like Q has one 768 by 768 matrix, and key has a 768 by 768 matrix, and for value also it has a similar dimensional matrix. and these are the weights into this matrix, and it has a bias also that has 2304 values. So this 2304 is the 768. If you multiply 768 with 3, you'll get 2304. So those 3 square matrices are there. And when the embedding comes, embedding is it is a dimension of 6 6 into 768, and this is the matrix. And then we will do a cross product. Then we'll do a cross product of 768 cross 2304, and then if you cross product these two matrices, you will get another matrix which has the dimension of 6 into 2304. So this is the output matrix after multiplying cross product, after doing cross product of these two matrices. And then this matrix you will add the bias. So bias has the dimension of 2304, and if you add this 2304 matrix, then you will get the same dimensional matrix that has 6 cross 2304 dimension. So this is the output matrix which has the three information q, k, and v for all those three matrices. So if you divide these matrices into 3 matrices, then you will get 6 into 768 and multiplied by 3. So 3 matrices are there, and these 3 matrices are so if you see here in this part, it has like this is colored blue, red, and green. So this blue has 6 into 768, and then so on. So for each token we got 1 into 2304, and combined all of these 6, we get 6 into 2304. So first we will understand this, and then we'll understand why this is done. After this, what happens here is, this is a attention head. Okay, before going into the attention head, it creates all these key, query, and value for each token, and we got this matrix. Okay, and that matrix here it has shown. Okay, first, before that, we have 12 heads here. Okay, so one this is for one first of the 12 heads, and each head, so if you divide this 768, so this 6 into 2304, so this is the final matrix that we got after after doing cross product and adding the bias. And this, so if you consider this as 3 matrices, then those are 6 into 768 and into 3. Okay, we got these 3 matrices, and each matrix goes through each head, but those are independent chunks of this embedding. So this 6 into 768 will get divided into 12 parts. So this 768, that is the dimension where we chunk the embedding. Those are independent embeddings. So if you divide 768 by 12, that would be 64. So if you hover your cursor here, you will get the vector as 64. So you will get 6 into 64. So this is the matrix, and then multiplied by 12. So this is the matrix you will get for this is combined for each token, and this is also multiplied by 3. You have key, query, and values. This 6 So if we in this diagram it is considered as so it has shown that each token has one vector which is 1 into 64. So like that 1 into 64 and so on, so it has 12 matrices. So this is the key. Sorry, uh, yeah, this is the key. And similarly we have the values 1 into 64 and so on, 6 values. And after that we have the query also, but I will go to the query after that. Before doing that, so here we need to multiply this key and query. So why do we need to multiply this? You can scroll down and you can see here key, query and value matrices. So here what it has done is if you see this part, step 2, multi-head splitting. So what I have explained just now, that each head process a segment of the embeddings independently. So so that's why it has divided this 768 into 12 parts for each head. So each head is getting 1 into 64 for each token. And after that each head we perform masked self-attention calculation. This mechanism allows the model to generate sequences by focusing on relevant parts of the input while preventing access to future tokens. So we will go into each part one by one. First, what it does is it does a dot product. And if you see here, if you see in the figure itself, this key we need to transpose it, right? So if we transpose this 6 into 64, okay, if we transpose this, then we will get 64 into 6, right? So this matrix we need to do a dot product. Value is 6 into 64, and which will get dot product with 64 into 6, and we will get a matrix of 6 into 6. So in this diagram also, if you see, it has 6 values. If you click on this part, it will show what are the functions that is going on in the attention layer. So first it does a dot product. So after doing the dot product, you will get a 6 by 6 matrix. A mask is applied to the upper triangle of the attention matrix to prevent model from accessing future tokens. Okay, so one mask will be multiplied with this dot product output, and after applying the mask we will get only half part of the output. Others will be infinity. So if you see here, setting those values to negative infinity, the model need to learn how to predict. So this is in the training, need to learn how to predict the next token without peeking into the future. So it doesn't have to see what. So if we are currently at the point of data token, so it doesn't need to see the visualization token, it has to predict the token, right? So it so that information we need to remove from the attention layer. That's why that is got masked. And after masking, since we might get different like range of outputs after masking, that's why we need to apply this softmax. So here it is written that after masking, the attention score is converted into probability by the softmax operation, which takes the exponential of each attention score. So this attention scores we need to apply the softmax, and after, as you know, softmax will give us the output values between -1 and 1. And if you hover over any dot here, any number, you will get a value which is which is below 1 and above -1, like 1 and a 0.84, 0.63, so on. So after doing all of this, we here there is no dimensionality change. We are still at 6 cross 6 matrix. So this is done in the attention block for each. So like this attention block, we have 12 heads. If you go into the next head, you will get similar kind of output. But one more thing I need to explain here, the value matrix. Okay, so if you click on this value matrix, you can see how for each value the attention is getting used. So in this part, what we are doing is we are doing a cross product of this attention with the value matrix. So here we got this 6 cross 6 matrix, and this 6 cross 6 matrix got will do a cross product with the 6 cross 64. Okay, so this 6 here we will get an output of 6 cross 64, right? So this is the output for each value, right? So each attention head will have different information, because those are independent values. So for each attention head, this value is got cross product, and then this will have the information of what kind of attention we have for this specific value. Okay, so similarly we will have the information for each head, and each head will give us different vectors, 1 into 64 vectors, right? So sorry, not 1 into 64, 6 into 64, as we have seen here, 6 into 64. So 6 into 64, that means 1 into 64 for each token. So after getting this value, we concat everything. So this 6 into 64, we have 12 matrices, right? So these 12 matrices, if you combine all of that, we have 6 into 768 again, right? So this is whatever the input was, we got the same output, right? So this output will now it will go into this MLP layer. This is multi-layer perceptron. So this multi-layer perceptron, what is the significance of this layer is it is written here: after the multiple head of self-attention capture the diverse relationships between the input tokens, right? So the concatenated output, so I have told all of the output of the heads are concatenated, and that is getting passed through this multi-layer perceptron. So this multi-layer perceptron, this name is a little bit complex, but this is nothing but a feed-forward network. So what it does is it increases the dimensionality and then decrease the dimensionality again. It is written here, the first linear transformation, it has two linear part. One linear transformation increases the dimensionality of the input fourfold. So fourfold means 768 multiplied by 4. So this output that we got from the attention heads will get passed through the MLP layer. So I'll just quickly show you something. Okay, so let's say this is the MLP layer, first part of the MLP layer, this is the linear layer. Okay, so when this goes through the linear layer, we will get dimensionality increased by 4. So this will get multiplied, let's multiplied by 4, and we will get a dimension of 6 into how much it will be, 3072. Okay, so this is the metrics that we got after passing through through the first part of the MLP layer. After getting this output, this goes through the second linear transformation also, which reduces the dimensionality again to 768. This is like decoder encoder part model. This increases the dimensionality and then decreases it again to the original size, which is 768. So let's write it like this, 4, and then we'll get 6 into 768. Okay, so if you click here, you will see a visualization how this is getting done. There is a matrix, weight matrix, that is 768 by 3072, which is get cross product with the embedding output we got from the attention layers. And after that there is a bias 3072, and then we got this embedding 6 into 3072, right? So this is the part, this is the dimensionality increase part, and after that the dimensionality decrease part is also there, where we have a transposed weights 3072 cross 768, and after doing the cross product of these two vectors, we get 6 cross 768 matrix, which is the same matrix that we got from the attention or before the attention also, right? So after getting this output, there is a layer normalization. So if you click on that, you will see why the layer normalization getting applied there. The layer normalization helps to stabilize the training process and improve convergence. It works by normalizing the input across the features. So from each head we get different kind of outputs, right, based on the key query and value matrices. So to normalize all those outputs, this layer normalization is there, so that we get normalized output, stabilized output that is going to pass through the next layer. And this after the layer normalization, we get the same vector, and we get the same vector, that is 6 into 768, right? So this 6 into 768, this matrix we got from the transformer, we just name it T1. Okay, so after the transformer block, so if you see here, it has transformer blocks, right? So if you see, there are here it is written that 11 more identical transformer blocks are there. So whatever we have seen all the layers in this block, this is getting replicated in the next block. So if you click here, the output of that block, so this vector, this is the output of the first block, right? So this goes into the next second transformer block, right? So this second transformer block also we do the same calculations, same layers are there, only like it has different matrices, and this will also give the same output, not same output, same dimensional output, so that it can go into the next block as well. So if you click, this third block is there, fourth block is there, fifth block is there, and so on. It will go till 12th block, and we'll see after the 12th block what happens. So this is the 12th block, this is the last block. As you can see, all the layers are same. After the residual, we do the layer normalization, and after the layer normalization, here we got the vector 766 into 768. So I'll also draw here. We will get T2, T3 and so on until we get T12. This is the last block, and here also the matrix is 6 into 768. Okay, so this is the output, and here if you see how we do the logic calculations. So this is the embedding, this is the last embedding, right? As you can see here, these are all the vectors, right? We are not taking all the vectors, we are taking only the last vector. So this attention block has been applied. Since that is applied, the information of the previous words are there in the last output, last matrix, which is 1 into 768, right? So this is the last block. We take the last block, and then that so let's say from this take last block, sorry, not block, last embedding, and the last embedding is 1 into 768, right? So this has all the information of the previous 5 embeddings, and that goes into the last logic calculation layer. And what this layer does is this has a projection weight. Okay, so if you click on this I button, you can see it transforms the final embedding into a vocabulary distribution. Parameters learned in training, fixed in prediction, right? So these are the parameters, these are the weights which will get multiplied with the output embedding, last output embedding. So we got this last output embedding, and we will do a cross product, and the last weights are 768 cross 50 cross 257, right? So after doing the cross product, as you can see, this 760, 768 and 768 is the same dimension. So what we will get is 1 cross 50 cross 257. All right, this is the matrix, last matrix we get from the from this logic calculation. And this will have the information of the tokens, right? So there will be multiple probabilities, right? So this is like 50 cross 256 probabilities. So if you click here, you will find how this visualized token got has been taken from this 1 cross 50 cross 257 output. So if you go below output probabilities, yeah, so here it is written that after the input has been processed through all the transformer blocks, the output is passed through the final layer, which I have shown. The final layer is 1 cross which has the weights 1 cross 760, 768 cross 50 cross 257, and that this layer projects the final representation into a 50 cross 257, 1 cross 50 cross 257 dimension, where every token is the vocabulary, has a corresponding value called logits, right? So every token, that means 256 257 into 50, how much is it? Let's do the math. 50 into 257, this is 12,850. So we have, so if you see here, we have 12,250 right? Sorry, 12,850. This much of losits, this many losits. So let's go back into this. Any token can be the next word. So this process allows us to simply rank these tokens by their likelihood of being that next word. We then apply the softmax function to convert the losits into a probability distribution that sums to 1. This will allow us to sample the next token based on its likelihood. So each token has a information, right? Each token has, sorry, each this 12,850 values has has a value, right, which is like minus something, 120 or 250, something like that. So there will be 12,850 values. So out of these values will get passed through the softmax. These values will go through the softmax to get the output between 1 and -1. So let's say the first one is 1 and minus, sorry, 8, sorry, point 8, point 6, minus point 3, and minus 0.8, right? So this is the final matrix that we get from the model, and these losits, these are the losits for each token, right? So this is like, this has like how many, to 12,850 tokens, right? So out of these tokens we will get the highest probability embedding. Let's say this is the first one. So out of this 12,850, the first token has the highest probability, so we will get the zeroth index token. So we will have a token chart where each token has a token 1, token 2. So each token has an index 0, 1, 2, so on. So if we get the index as 0, then we will take this token 1, and that will go to the output. That will be our output. So after getting the softmax, we check in the tokens table, and then we give that token as an output. So here that is happening. In this part, this, if you see, this token has a different IDs. So this is the ID 3,800, 38,350, and that will get checked in the tokens table, and then from the tokens table we get the token which is visualized, right? So this is pretty much it. This is how the transformer model works. I hope you have understood what is going on inside the model, and yeah, stay tuned. Thank you for watching.